So thought it would be nice, we thought it would be nice if we swept aside the old fogies for a while and heard from some of our younger participants here. And if you are interested in also doing one of these half-hour talks, and you haven't already given one, say, in a workshop or something like that, please let me know. Okay, so Augustin Moinat is the first of our three with this marvelous title. Go for it.
Thank you for this opportunity to talk here. So I'm going to be talking about some results we're going to be publishing very soon about space and localization for a dynamic 543 model. So the theory for 543 model, so I'm going to start at a bit of the bibliography. The theory of regularity structure developed by Martin Hare in 2014 gives some local theory for solutions of some rough and singular stochastic PDEs. And for the 543, well, we have also some elements that we're going to be using in our as assumption for our proof in this paper by Kateli and Chuk. The next one by Felix Otto-Girasor, Scott Lipp, and Henrik Weber gives us some technical tools that we're going to be using for our PD arguments. And the next three references are just to mention that our result is not completely new. There are some work that have been done. So first thing by Christophe Morin and Henrik Weber, but gave some results for the 543 model, but only on the torus. And then but these two results are give global solutions on the full space for the 543 equation. So the result I'm going to be talking about today is a joint work with my supervisor, Henrik Weber, and it's going to be on the archive very soon. So right, the 5-4 equation. The 5-4 equation is just stated as such. So we have here a white noise psi, which in dimension 3. I don't know how which in dimension 3 is a distribution of regularity minus less than minus 5/2. So phi in particular is expected to be not a function but a distribution. So the cubic term, the cubic nonlinearity is not well defined for distribution. I don't have in the classical definition of products. So we need to subtract some term which we denote formally by an infinity times phi, or to add some term to subtract the cube. Right. So what this means actually is that we're going to be working with a regularized equation. By setting a regularization of the noise, which we denote by zeta, and the infinity becomes these two constants C1 minus 9C2, and these two constants are going to be depending on delta, but our whole work is going to be proving bounds on the solution U that are independent of delta. So we, from now on, everything is going to be well defined because it's all smooth functions because we have some regularization. But we're going to prove something that don't depend on delta. So this is going to be where our regularity, up to what regularity we can measure some of the terms. C1 and C2 will diverge when the regularization is removed, but that's not something we concern ourselves about. This is in our assumptions. So, for example, well, the first thing we want to do is to look at the linearized equation when we remove the u on this side. So we just have this, and the regularity we allow ourselves for this term is just minus 1/2 minus. This should be just 1 epsilon, not 3 epsilon. Okay. Now we want to look at the cube, so it's a good idea to look at the square and the cube of this linearized thing. And here is where we define, if we can put the,
You have to pull the string. Pull this.
Oh, that's good. Right. So and so we define this square, this renormalized square by subtracting the constant C1, and this is to make it so that it converges as delta goes to 0. But we just assume that we have a bound on this in this measuring this regularity, and same for this one for this other renormalization. So with this, we can already define what we call the Bush approach, which is just looking at U minus the solution to the renormalized equation, which satisfies this equation, where you see that the constant C, when you expand the cube of U, which is V plus this multiple, you see that these constants were introduced exactly to get the good, to make a these terms appear here. And in dimension 2, this term is of slightly higher regularity, and this term C2 is not needed to define solutions. And so this in dimension 2 is enough for the solution. In dimension 3, it's not enough, so we need to go higher in the expansion. And we do that by integrating the terms we have just defined and assuming these regularities. And we want to introduce more, so we want to multiply these things with the terms we had before and also with polynomials. So x here denotes just the projection onto the space coordinates, because I haven't said that y is always going to be a space-time coordinate, and x is the projection on the space coordinates. So for these products, we need to introduce some negative renormalization. Once again, it's subtracting this constant to make something converge when the regularization delta is brought to 0. Some of these terms don't need any renormalization, but that's just how it is. And now we have this key idea of theory of regularity structure, is that we don't look at object at points, but we actually look at description of local description of object up to some regularity. So for example, for this polynomial here, well, we want to look at it as so that it vanishes at the right upper group when x goes to 1. This is called positive renormalization. Right, so now this doesn't make sense because here I have something only depending on 1, and here I introduce something on x. What we're actually going to do is we're going to assume some bounds on these quantities. So here I have just the same thing that as I had before, but I have tested it against a test function that is rescaled according to the parabolic rescaling, which comes from the heat equation. And so for all of these I have tested like this, and I assume that when you integrate it, you get a blow up that is with these exponents, which are the regularity I assume on these objects here. Right, so now I have all the ingredients I need to state my theorem, which is these definitions of norms. And this is the theorem. So I have recalled the equation that V satisfies. And I say that if V solve this, so this equation, pointwise on P. So P is just going to be a bounded domain. So for example, I'm going to take a space-time rectangle. So it's space-time bounded domain. Then I have a bound on VPR. PR is the same rectangle, but slightly smaller inside with respect to the parabolic distance. So in time I would have r squared. So this is time, and this is space. And so I have a bound for this VR that is a max of 1 over r, and then all the assumptions I have made on the other trees, with gamma of tau being the regularity I was assuming on these trees, and n of tau is here in the exponent is simply the number of occurrences of the noise in the tree. So. So what does this bound tell us? Well, it's the first thing you can see is that well, this doesn't depend on the domain P. The noise, we only care about the, also it's a localized bound, so we only care about the regularization of the noise on the domain P, or maybe a slightly bigger domain to obtain this. And then if we want to define solution on the full space, well, we see that at any point you can say that you have the solution locally, and this gives us a general theory for the solution. Right. Also, we get some probabilistic integrability. So in the case where this is actually white noise, we expect to have these kinds of exponential integrability, which translates exactly to this with another constant lambda. So this is almost an straight exponential integrability. We just have this minus 2 epsilon, which makes it fall just short of some maxims needed in quantum field theory. Maybe there's going to be a way to solve that, I'm not sure. Right, so now I'm going to go a bit into the proof of the theorem. So as I was saying before, the theory of regularity structure is a very local theory. And for example, it doesn't, this minus sign here is not, doesn't matter in the theory of regularity structure to define solutions. But if you just look at the ODE v prime equal minus v cubed, or v prime equal plus v cubed, v prime equal plus v cubed, you expect to have blow up infinite time. You have v prime equal minus v cubed, you have the opposite. If you, however high you start, you're going to come down to 1 with this same bound 1 over r as we have here. So we want to use that, but to use that we also need to have the remainder term being bounded. Well, here we don't have it, but we convolve the equation with the same site we're using to define our regularity earlier. And when you do that, you just produce a commutator term. Here, the other terms are just the same one convolved with t. So now we have some PD maximum principle, which gives us, so we have this 1 over r bound, and then we have all the terms on this side with the power 1/3 everywhere. We have grouped them like this. This E has the C2 in it because some renormalization is going to be needed to define this product. So the first observation is that with all the continuity, you can go from V convolved back to the normal V. And same here, you can bound this by this quantity here. And finally, this was our assumption on this tree that it was bounded. It was afforded 3/2 minus 3 epsilon. Okay, so now I'm going to concentrate. So the two terms we haven't defined are this one, and I'm going to concentrate on defining this one. So here we want to define a product, and this is going to be in this same as before. So to define products, we need to look at local expansions around some base point, and so we have this, and so we're gonna see how we're gonna guess a local expansion for this product based on a local expansion for V to define this product. So and we have this reconstruction theory. Also, the theory of regularity structure reconstruction theory tells you that a guess for the expansion is actually a good guess for the distribution itself. In our framework, this theorem is quite simple. So if we have, as I was saying, so this is our good guess. We assume that we have some regularity control close to the diagonal. Always testing with this this function psi t. And then the function on diagonal actually also satisfies this kind of regularity with we have what we have paid in beta here. Well, it comes back to this for T gamma. So the proof of this theorem is quite simple. It's like 2 paragraphs, but it requires a special choice of kernel psi t to make it very simple. And the kernel psi t would have this property which allows us to look at something at one scale by something at the same scale. Well, the scale divided by 2, and we have another kernel. This kernel has to be like just smooth and positive, have integral 1, and compactly supported as well.
So it has to be a semigroup then, doesn't it?
It's not a full semigroup property because it's only on dyadic scales.
Oh, I see.
That's the only thing we need to prove this theorem. If we want to have a full semigroup property, then you cannot have a full semigroup property and compact support at the same time.
Yeah.
And compact support is quite important if you want to prove local bounds. So this is how we do it. Right, so back to defining this product then.
Is this the product that comes about from the commutator?
No.
No.
No, okay, let me go back to here. The commutator was this thing.
Yeah.
So it's V human, and this this you can just bound by using the Holder norm of V times V squared. This is this term that we want to bound, which
This is because V is a function.
V is a function.
Yeah.
It's just of regularity 1/2 minus 3 of time. I mean, everything is a function, but
Right. Yeah, but it's really a function.
yeah. Exactly. Right. So we want. So as I said, we're going to guess the expansion of this product by looking at the expansion of V. And so this is what we do. So the terms I have added here, I subtract them just below, and then there is if you look at it here, you see that the C2 V everything cancels exactly. Everything is perfect, just in identity. And now we have that. Well, the terms we have added and subtracted are actually exactly the definition we had given before, here and here. This is what the full expansion of V, we'll call it u of x and the other variable. So this gives us this guess for the definition of the product, which is this first line times that, and we also have the C2 V of x here. And well, essentially, in the theory of regularity structure, all this is done with some algebraic machinery, which is very, very systematic. Which is also why we want to do this proof in this framework, because we think it's going to be easy to expand it to other equations where so far we only have local theory. We want to get global theory. So right. What this slide says is that it actually works very well. So we have this. If we look around the diagonal, we have this expansion here. Here you can see again the same definition of the product we had before. Here you have also this definition of the product with x, with the linear functions. And this gives this bound. So we just have this is this term. The u here gives this term. So yeah, as I said, this is all done very well in the framework of a regularity structure, and it just allows us to get this down on this definition of the product. So we have the terms we just got from this expansion, and then the terms we had added and subtracted before. Okay, well, I haven't told you what this quantity is. Well, there's also the nu here. Nu was the coefficient we put in front of the polynomial. Should have mentioned that. And well, for the definition of this product, well, we have done all the work here with this framework of regularity structure. What remains to be done to finish the whole proof is well, we need to get Charter estimates for these three quantities. So this is what the part that was inspired by this paper from Felix Otto, Sarah Scott, and Henry Quever. Then one part that's quite interesting in the proof was the choice of T for the maximum principle. So you remember when we said that we would convolve the equation to get something which we could control on the right hand side. The T that we choose at that point here is not just any T, it's actually chosen depending on the solution itself. So essentially we will have T is 1 over the norm of the solution. And well, so this is one of the things I'm not getting into depth onto that. And also the part that was very fiddly in the proof is the choice of the domains for the norm. Because every time you take a convolution with something at scale T, well, you look at on a slightly bigger ball, which on the small ball around the point, which is of radius T, and you have to be careful that all these balls you can close the argument. But yeah, those are the remaining ingredients for the proof.
So you have to change the norm on each iteration a little bit.
Yes.
And it changes by less and less as you do it more and more.
Yeah.
Mm-hmm.
Yeah, it's a bit. It's quite a bit of a tricky part of the argument. Yeah. All right. Well, I'll stop here. Thank you for your attention.
So actually, in your slide, there are two T. One T is just the generic one in the reconstruction, but then the T you use in the maximum principle is finite. No, it's chosen.
There's this T that we choose in the maximum principle.
Yeah, there is this one, and then the next slide, this T is.
At this point, even from here, the T that we have for this assumption. This assumption should hold for every T smaller than the T we have on this one. And then when you
maybe it would be useful to give the other a specific name, because otherwise it's never clear if you're talking about a generic T or that cutoff you want to use.
Yeah.
Because at some point you have estimate where T appears with negative power. Now that's why you cannot send it to 0.
Yes.
Yeah, here. No?
Yeah. So this one is with the T that's from the maximum principle exactly. So this one we don't need to send it to 0.
So when you're using the maximum principle, I mean, there are two ways of arguing that, and one doesn't sound like it would be a nice way, which is to talk about derivatives being positive or negative at maxima. Are you just using the positivity of the Green's function? I mean,
no,
d by dt minus Laplacian, or using something more?
No, it's for this. We look at the maximum principle. Yeah. So to prove, well, if we have an equation like. dt minus operation of v equal minus v cubed plus g.
Yeah.
And then from that you can get a bound that norm of v is bounded by 1 over r and norm of g equal to 1/3. The proof is really just getting a smooth version of this maximum.
Mm-hmm.
and then dividing v by that, and then with some, you have to say that at the maximum the derivative of that quantity is going to be
So you do
zero.
argue with Drew's. I thought you might just be able to say that the inverse of d by dt minus the Laplacian is a non-negative function, and when you write the Green's function, the right-hand
No,
side.
because it's local, you cannot reason with the green function.
Oh,
Then
you
you're
cannot?
lost.
Oh, of course, all right.
You need the cube, right? The cube is the thing
It's
that
the
helps you.
cube.
I see. Well, yes, I know that the cube has to help.
That's
But
also-
that should take out the Laplacian. I mean, roughly speaking, I'm expecting that.
But the Laplacian will not give you a problem, no? Because at the maximum is give the right sign.
That's what I mean, right, yeah,
And the derivative is also the right sign.
right.
And so you are just saying that,
You also use that the gradient is equal to 0.
yeah.
So you
the
didn't
gradient-
do
yeah,
that
you-
way, I see, okay.
that's why you need a classical solution.
Mhm.
Yeah, so because else you don't have the v infinity.
No, I mean, you can have a bounded function, but if the equation is not satisfied classically, you cannot say, I mean, it has to be C2 for
Right.
that to work. Otherwise, you cannot.
Okay, thank you.